All right, today we're jumping into a story about a molecule that is so perfectly shaped, it feels like it was dreamed up by an ancient philosopher. But it's actually at the bleeding edge of modern science. So, what's the connection?
I know, it sounds like the start of a really nerdy joke, right? But the answer is actually fascinating. It all comes down to this shared obsession with perfection, a hunt that connects Plato's perfect shapes with the actual molecules being built in labs today. And the thing that ties them together is a shape.
And this is it. Say hello to dodecahedron. Yeah, the name's a bit of a mouthful, but the structure itself is just pure elegance. It's a molecule, C20H20, where 20 carbon atoms lock together to form a dodecahedron, one of Plato's 5 perfect solids. It's like an ancient mathematical idea made real.
So, how in the world did chemists manage to go from one of Plato's abstract ideas to actually building this thing, atom by atom? Well, it meant they had to become tiny molecular architects.
Dodecahedron isn't totally alone. It's part of this super exclusive club called the Platonic Hydrocarbons. And get this, so far, chemists have only been able to build 3 of them. There's tetrahedrane, which is this tiny little pyramid of 4 carbons. Then you've got cubane, a perfect 8-carbon cube. And finally, dodecahedron, the most complex one of them all.
Okay, so let's zoom in on our star of the show. Because it's not just a pretty shape. Dodecahedron has some really cool properties that have scientists totally fascinated.
For one, it's got this awesome title. It's the smallest fullerene possible. You've probably heard of fullerenes, like the famous buckyball. They're these hollow cages made of carbon. Well, dodecahedron is like the blueprint for them all, a perfectly sealed cage where every single one of its 20 carbons is also attached to a hydrogen atom.
And the design is just so simple and beautiful. It's just 12 pentagons, these 5-sided carbon rings, all stitched together to form a perfect little sphere. It's this incredible symmetry that makes it so special, and as we're about to see, so much fun to mess with.
But here's where things get interesting. Just because a shape is geometrically perfect, that doesn't mean it's, relaxed. Turns out, these beautiful little cages are holding on to a lot of hidden tension, a kind of pent-up energy that chemists are dying to figure out.
That tension has a name, strain energy. The best way to think about it is like a bent spring. See, carbon atoms have a favorite angle for their bonds. When you try to force them into a tight shape like a cage, you're bending those bonds away from where they want to be. And all that energy you use to bend them gets stored right there in the molecule. Now, to really see this strain in action, let's bring back its cousin, cubane. Remember, cubane is built from squares, 4-membered rings, which forces its bond angles into a really tight 90 degrees. That is a ton of strain. Dodecahedron, on the other hand, is made of 5-membered rings, which allows its bond angles to be much closer to their natural, happy state.
And wow, this chart just lays it all out. Look at that difference. Cubane is packed with a whopping 154.7 kilocalories per mole of strain energy. Dodecahedron is way more stable, with less than half that amount. So yeah, it's a perfect shape, but it's also a pretty chilled out one, all things considered.
Okay, so this is where our story pivots. We go from just admiring this perfect shape to actually trying to re-engineer it. Scientists started asking, hey, what if we tried to build this cage with different Lego bricks?
Which brings us to the big question in the research we're looking at today. What happens if you take that perfect dodecahedron cage and you swap out half of the carbon atoms for silicon atoms? I mean, silicon is carbon's next-door neighbor on the periodic table, so what could happen?
Well, what happens is the complexity just absolutely explodes. Just by swapping 10 carbons for 10 silicons, it turns out you can make 1,648 different versions or isomers of that molecule, each one with a totally unique pattern of carbon and silicon atoms. And here is the big reveal. After running the numbers on all 1,648 versions, the researchers found something huge. Where you put those silicon and carbon atoms isn't just a small detail. It completely changes how stable the molecule is. The arrangement is everything.
This table really breaks it down for us. Check it out. The most stable versions by far are the ones where the carbon and silicon atoms are spread out as much as possible, creating the maximum number of carbon-silicon bonds. But if you clump them together, creating little patches of silicon and little patches of carbon, the molecule becomes incredibly unstable. We're talking over 120 kilocalories per mole more unstable. It's a huge difference.
So you might be thinking, okay, cool, but why does this matter? Well, because learning how to build and fine-tune these tiny cages could unlock a whole new world of technology. I mean, think about it.
If you can precisely place different atoms on these little frameworks, you can start to design molecules that do specific jobs. Some of these new silicon-carbon cages, for example, look like they could be amazing molecular-scale semiconductors. That could completely change electronics. We're literally talking about the building blocks for the materials of tomorrow.
And this is where it really feels like we're living in the future. Everything we learn from studying cages like dodecahedron directly feeds into the wild world of nanotechnology. This image here? That's a nanocar, a single molecule designed to work like a car, and it uses fullerene cages as its wheels. This isn't science fiction anymore. This is what's happening right now at the frontiers of science.
And that just leaves us with this final thought. We started this journey with an idea from ancient Greece, and we ended up with a wheel for a microscopic car. It just goes to show you that there is a whole universe of possibilities hiding in the most basic science. If one single perfect shape can teach us all of this, it really makes you wonder, what are we going to build next?